Now, step 1 is done, and we continue executing our plan. We're now on step 2. So let's assume that B and C are mu measurable, and then our goal is to prove that their union is mu measurable. Then by induction, we will have proven that A mu is closed under finite unions. And with steps 1 and 2 in hand, we will finally know that A mu is an algebra of sets. So that's the result of part 2. Step 2 is that we'll get that A mu is an algebra of sets. Okay, so these are mu measurable. I'm trying to prove this is mu measurable. Let epsilon be greater than 0 for the sake of proving this is mu measurable. Well, B and C are mu measurable, so they can be approximated in the sense of outer measure by sets that are in our original algebra of sets A. So there are, let's call them A sub B and A sub C in our algebra of sets A, such that the outer measure of A sub B, delta B, and the outer measure of A sub C, delta C, are both less than, we can choose any positive number we want here. I'm choosing epsilon over 2, where the epsilon is this epsilon that got fixed at the beginning for the sake of hopefully proving B union C is mu measurable. Now, what do you think you would want to use to approximate B union C using an element of our original algebra of sets A? You probably have something in mind. You're probably thinking of AB union AC. So AB union AC is definitely in the algebra of sets, since the algebra of sets is closed under unions. And so it's very natural to think about using this. And to do so, you'd have to think about this symmetric difference, right? AB union AC, symmetric difference, B union C. Is this related in a nice way to the to these individual symmetric differences whose outer measures we know something about? Yes, but not so directly. We just have an inclusion in the direction that's useful, not necessarily an equality. So we end up with this inclusion. AB symmetric difference B union AC symmetric difference C. So that's the extent to which the set theory helps us here. And as usual, I'm not going to write out a detailed proof, but I do like to think through these fully just to make sure they're right. So let me do a sort of schematic sloppy proof where I chase an element around. So let's say X is in this thing. Then there are two possibilities. So let's start a case tree. So one case split here. If X is in this symmetric difference, either X is in this one and not in this one, or it's in this one and not in that one. So these are the two possibilities. And each of those splits into two possibilities, since you've got X in a union here, so it's either in one of the two things being unioned or in the other one. And X is in the union here, so it's in one or the other. And the goal is in each of these possible cases at the bottom to verify that X is in here. So if X is in AB, since it's not in the union B union C, X is not in B, right? So that means X is in AB, but not in B, which is good because that places it in this symmetric difference and therefore in this union. Similarly here, X would be in AC, but remember it's not in B union C, so it's not in C. So that places it in this side. And then here X would be in B, but since it's not in this union, it's not in AB, which places it in this symmetric difference. And here X is in C, but not in AC, since it's not in the union, and that places it in this symmetric difference. So no matter what, we end up concluding X is here. All right, so that's out of the way. We've got this inclusion, and this inclusion is all we need since we're trying to get an upper bound, really, on the outer measure of this thing, right? So using the monotonicity of the outer measure, so that means using, where did it go? The general monotonicity of the outer measure here, since we're not using this one, we're using this one. It's proposition 15L1 part 2. We can turn this inclusion into an inequality. And now we're looking at mu star of a union. All right, but I want to be talking about mu stars of these individual symmetric differences. But mu star is always countably subadditive, right? So here I'm referring to lemma 154. I'm going to use that again. In fact, I'm only using finitely subadditive here. Sorry, too many pages. Okay. So I get at least less than or equal to this, and I don't have to worry about whether these are disjoint sets or not, because I'm just using subadditivity here. All right, and I've already got that each of these is less than epsilon over 2, so less than epsilon. And look at that. Here I've got B union C, symmetric difference, something that's in our algebra of sets A. It had to be an algebra of sets for this to work, right, for the union of two things to be in there. And we've got the outer measure of that being less than the arbitrary epsilon we fixed at the beginning. And so step 2 is done. So now we know that A mu is an algebra of sets on X.